share my desktop. So, today, we will start with an interesting data set. We call it Old Faithful Gazette data set. So if you put question mark and run it on console, so it will give you the basic thing. It's called Old Faithful Gazette data. It's a waiting time between eruptions and duration of the eruption of Old Faithful Geyser in Yellowstone National Park in Wyoming, USA. So if you go to YouTube, so let me just go to YouTube, and what I will do, I will say faithful, okay, faithful geyser. So this is the Old Faithful Geyser data. Actually it's in the Yellowstone.
Steve Jobs, Elon Musk, Ratan Tata, Birla, Ambani.
So this is the let me see. So if you look at it carefully, then this is actually Old Faithful Geyser and in Yellowstone National Park. And this geyser, it's a very hot water comes out, though it's a very cold area. And sometimes it goes really high it goes about for 3-4 minutes. This geyser goes for 3-4 minutes. This is definitely 2-3 floor high. It's very high. It goes very high. It's really hot, steaming water. So let us go back to the data. So what this faithful data is, it's give you two variables. One is eruptions, another is the weighting. Okay, and if you plot them, these two variables, so plot the faithful 20. So you can see the scatter plot. So on the x-axis I put the eruptions, and the y-axis I put the on the weighting, and you will see that there is a sort of a two subpopulation is going on. And then if you just do a histogram of, say, weighting, say weighting and probability equal to say true, then what happens? You can see that clearly there is a bimodal behavior. Okay, the histogram clearly tells us there is a mode somewhere around 50, 55, and also this is like 50 is somewhere here. So there is a, concentration, some concentration is happening here and some concentration is happening around 80, which is, if you do the histogram of like this, then this is the sum of the concentration of the at the 80. So it's a two, clearly it's a two bimodal distribution. It indicates there is most likely there is a two subsystem is there, two kind of sub-geo system is going on, and that is what, and this data is just a manifestation of two subsystem, most likely. I'm sure geologists, the earth science scientists are studying these geyser for a long time, and they might have some reasons which I'm not aware of. But just looking at the data, we can definitely say that there is most likely two subsystems. And how those subsystems works and all these things, that of course needs a lot of experiments, scientific experiments, and like, so our and validations, data collection, and all those things will be there. Now, set aside all those things. Question is, if I just want to fit probability distribution on the weighting variable, what kind of distribution you'd like to choose? You'd like to fit? Any idea, guys? Let me, some mixture distribution. Okay, there is one thing called some mixture distribution. What do you mean by mixture distribution here?
Sir, it's like a combination of discrete and continuous distribution, or so like, or it can be like, yes, essentially it's a combination of discrete and continuous distribution, but like we decide there are like two parameters to adjust the amount of weightage we take from each of those distributions.
Okay.
And these parameters are adjusted according to the data. Like we try to fit the distribution to the practical data by tuning these parameters.
Okay. And why discrete? Because look at the waiting time. It's a time, so it's a continuous. Why you want to use a discrete distribution there?
Sir, like
Do you have any example in your mind which leads you to believe that it will be a mixture of two distribution, or mixture of continuous and discrete?
no,
You
sir.
seen any example before? No. Okay.
Actually, like if we want to work with two continuous, I mean, if you want to work with a purely continuous distribution, then we just have beta distribution with parameters 0.5 and 0.5, which will give us a bimodal distribution. It's somewhat a U shape, I think. So like it was intuitive that I have to
Sense.
use
Okay, fine, fair enough.
Sir, or maybe we can take the sum of two Gaussian distribution.
Some of the
Yeah, exactly. Two
Gaussian.
normal distributions.
Two normal
normal distribution. Yeah, very good. So agree. So the suggestion is we will take some mixture of two normal distribution. Okay, let us try. How can we do that? Mixture of two normal distribution. Okay. And how will you make this? So it will be a new distribution, right? if you are saying it's a mixture of two distribution, how will you make sure that this distribution will be actually a distribution? The first thing you have to propose that yes, this will be indeed a distribution. Huh?
Take the average of the. So we can take average of the two normal distributions, ensuring that the
that will give you
area under that
average. That will give you average. Okay. So what I
So
mean by that, how to ensure a distribution, a function is indeed a distribution. So first thing you have to show first, say suppose I have to first define a PDF. Okay. Probability density function. Probability, then first define step 1, define a density function. Okay. So how I will do that? So the first thing I'm going to do is I will say that, okay, the distribution will have a PDF f of x equal to some p times PDF of say f1x plus, my chai is here. Thank you. Just a minute, please. अल्प चाहिए अल्प हाँ दिया था अल्प बोला था थैंक यू वन माइनस पी एफ टू एक्स where okay there's some chat are coming in. Weighted average would work then yes normal one. Okay, fine. So where thank you Vimalda. Where if one x is PDF of say normal distribution with some mean mu1 and variance sigma 1 square. Similarly, you can say if 2x is PDF of normal mu2 sigma 2 square. Okay. So this is I'm just I took two PDF. If 1x is a PDF probability density function, if 2x is another probability density function, I'm taking a weighted average of them, correct? And I'm saying that this gives me a function, and I'm claiming this is also a PDF. Okay, just claiming is not enough. So now I have to show this is indeed a PDF. So how can I show that?
sir, this is a convex combination. So like if we integrate fx, basically we are integrating over f1x. Yes sir, it will be 1 because integration over f1x will give us 1 and f2x will also give us 1. So p minus p will get cancelled and
you will be left with 1, but you will need one more condition. The condition is p is between 0 and 1, then only that will satisfy. Okay. Acha. So that you have to so are all of you with me? Huh? So basically you have to show two things. One is is you show f of x is greater than 0 for all x, and B, you show f of integrate f of x over R, and that should be 1. That is all you have to show. If you show these two things, you are all set. And you should be able to show these things. I'm leaving it for you to just check it. Okay. Acha. Next idea is, how do I know this distribution is actually going to give me somewhat representative distribution of what I'm trying to model? See, acha, tell me how many parameters are there in this new distribution that I just defined?
5.
5 parameters. Mu1, mu2, sigma1 square, sigma2 square, and what is the 5th parameter?
P.
P is the 5th parameter. Very good. So my number of parameter is number of parameters is equal to 5. Okay. So let me call this as a theta. So it will be basically mu1 sigma 1 square, comma mu2 sigma 2 square, comma p. So these are the 5 parameters I'm going to. So I have to estimate these theta vector or the parameters from the data. Okay. And unfortunately, method of moments type estimators will not be working. So the only methodology that will be available to us is likelihood estimation method. So we'll use likelihood estimation method.
That would be mu2.
Uh-huh.
Third parameter should be mu2.
Yeah. Correct.
mu2 and sigma
mu2, and here it will be sigma 2 square. Yes, correct. Acha. Next, what I'm going to do, before even I try to model this likelihood estimation and all this methodology, what we can do, we can make some educated guess whether it is even representative model for modeling this kind of data. So my one normal could be, I can think of a normal, this is one normal, this mode is one normal distribution with somewhere mean is around 50 and with a standard deviation. Can you make an educated guess what would be the standard deviation of this distribution? The first one, the smaller mode. Look, the most of the values are somewhere between 40 and 70.
Sir, 3 sigma is 15. So sigma should be
Somebody saying 5.
yeah.
Okay. So what I'm trying to say here, even if you take, so basically the intuition behind this 5 is maybe I can take the mean is around maybe 52, 53. I'm just throwing some numbers. Don't take it any, seriously. Now the range, let's look into the range. Range is somewhere between 40 and maybe 65. 40 and 65. Okay. So if I say that here somewhere I have a mean and then 2 standard deviation is this guy and of the right of the mean, and 2 standard deviation left of the mean is this guy 40, then total difference between 40 and 65 is somewhat 4 standard deviation. Okay, so I'm just making a ballpark kind of educated guess. So the standard deviation will be somewhat, I'm just making educated guess as 62 minus 40 divided by 4. So maybe 6.25. So 5 was a approximately good guess. So maybe I will just take 5 or 6, 6 or 5. And looks like this is also going to be the same, 6 or 5 or 7, something like that. Now what I'm going to do, so let us take a model, say, let's take p equal to 0.5, mu1 equal to say 52, 53, sigma 1 could be 5, mu 2 could be near about 80, and sigma 2 could be, let's take 5 just for fun. Okay, now what I'm going to do, I'm just going to, so this will be the parameters of this value of the parameters of this distribution, and let's just plot this distribution over this histogram and let's see what happens. So so what I will do first is I just do a sort kind of thing, then make a histogram. X probability equal to and then color equal to maybe blue, then not sky blue, let us take sky blue. Then we can take x lab equal to weighting. Okay, so let me just redraw the histogram, and then let's draw the lines. So first what I will do the f equal to p into d norm x mean equal to 53 and is equal to 5. Okay, and plus 1 minus p. So there is something in the chat. Why did we sort? Why did I sort this? Okay, I'll tell you why I sort it. It will create some sort of a problem. I'll show you. If you don't sort, then your when you try to draw this line, it will create some problem. I'll show you that. So sorting is little bit required just to draw the point, because what happens is it will take the point and then it will take the whatever second point you have in the database and it will draw a joint. So if you are not sorting, then it will first will, if you have a point here and if you have a point here, then it will just draw us, like if you have a point say 40 and then next point in your vector is say 80, it will draw a simple straight line between the two. But if you have sorted it, then 40 and then you have a 45 and then it will try to join this thing. So that way the line finally I will try to draw, that will become nice. So if you don't sort it, and we'll run without sorting and with sorting, and you will see the problem if you don't do the sorting when we'll try to draw the histogram. Okay. Denorm X and mean equal to 80 and SD equal to 5. Oh, I have to do P equal to 0.5. Okay. So so now I have, right, and now I will do a line. X comma F, maybe color equal to red with line width LW2 is 2. So now you can see this is the graph that we are going to draw, but clearly it is not a very representative because my P is just ad hocly chosen, my mu and sigmas are ad hocly chosen, but it has the potential to model two modes. If your data have two modes, if your data have two clusters, mixtures of distributions have a potential to model two clusters or two modes. So that is an important feature of mixtures of distribution. Okay. So now, we are confident that yes, this mixture of these two distributions has a potential to model these two modes. Of course, we have to estimate the parameters more correctly. That is a slightly difficult task. For that, we will resort to likelihood estimation method. Acha, question is, why are we sorting? If you don't sort this, then the problem typically that we face is this. Because what is happening, first it got a value here, then in your database another value is here. So it is just taking this if the density and this density and trying to draw a straight line. So when it try to draw a straight line, so when I'm using this line comments, basically it takes the two consecutive points and try to draw a straight line between them. But if I put the sorting, then what happens? If I do the sorting of X, it takes the 40 and then next value would be 42 here and here. And then corresponding PDF will be, they are next to each other. So corresponding PDF will be like, whatever that thing. And then it is joining the straight line accordingly. So that way the density is coming very nicely. Is it clear to all of you? Huh? Okay, good. All right. Next, we are going to say that this is step 1. We are done with the step 1, defining our distribution. And then step 2 was intuitive verification. The model is a good candidate model. Okay. Step 2 is some kind of intuitive verification, that the model is good candidate model. Okay. Next is step 3. Step 3 is now we are going to use the likelihood estimation method to estimate the 5 parameters of the proposed bivariate mixtures of two normal. Likelihood or maximum likelihood estimation to estimate theta. My theta is these parameters. Okay, these are the parameters I'm going to estimate. Okay, very well. So first thing what we have to do, we have to write the likelihood function. That is the first thing we have to do. So let's write the likelihood function. Like actually we should write the negative log likelihood function, right? So we will write negative log likelihood. And why we want to write negative log likelihood? Any idea? And not log likelihood.
Sir, because the function is like we have to maximize the function.
That we will do. So the first thing why we want to work with log likelihood and not likelihood, because remember that these density functions are typically many of the values are, you can see the values are coming very small. Each of their values are coming very small. Now we have 118 data points, about 150 data points. When we will product them in the likelihood, this will become smaller and smaller and smaller, and there is something called floating point error problem. So after a while, computer will say that, oh, I cannot handle smaller value than this, I will make it 0. So it will make all the likelihood values 0. So in order to avoid that problem, we take the log likelihood. Okay, and it's a one-to-one function. So maximizing likelihood function is equivalent to maximizing the log likelihood function. Okay, so that is one of the reason of, that is the main reason of taking the log likelihood, or working with the log likelihood. Now, why negative log likelihood? We are
To
going
make
to
the output positive.
huh?
To make it positive.
Make it positive. Actually, my reason is even more sharper. We are going to use the function called optim. Okay, which will do the optimization. I don't have to do the write the optimization routine. In the optim function, by default, it does a minimization. So by default setup is a minimization. So if I do provide the function, objective function of the optimization as a negative log likelihood, minimizing negative log likelihood is equivalent to maximizing the log likelihood. Okay, so that is my reason I'm writing negative log likelihood. Okay. All right. Next.
So,
yeah.
So can you repeat what you said just now? Minimizing.
So I'm going to use this general purpose optimization function or optimization routine that is available in the stats package. This is the basic R package is available. I'm going to use that. Now in this optim function, by default, it used a function to be minimized, it says. Okay, by default setup is a minimization. Okay, so if I have to do a minimization, then I should provide negative log likelihood. Minimizing negative log likelihood is equivalent to maximizing the log likelihood. So let me write it down. Minimizing negative log likelihood is equivalent to maximizing log likelihood okay, that is equivalent to maximizing likelihood. So instead of directly maximizing likelihood, so our objective is to maximize the likelihood estimates. Okay. But we cannot do that directly maximize likelihood because we will run into floating point error problem. So in order to solve that, we said that, okay, take the log likelihood, that will give me the same solution, exactly same solution. Because this log likelihood is just one-to-one function. This log is just one-to-one function. So I don't have to worry. Then we face the optimization subroutine that is available in R is do a minimization. By default setup, it does a minimization. Otherwise, I have to go and change the function. I don't want to do that in a negative. So instead of doing that, I can just write negative log likelihood, and I can run a minimization of negative log likelihood, and the solution from minimization of negative log likelihood will be exactly same as the maximization of likelihood. Okay, so this is the reason. Okay, clear, guys? Okay, so first thing first, we will write a negative log likelihood function. In negative log likelihood function, two things will go. One is theta, another is data. Okay. In the data, what will go? In data, it will go the x, only the x. Okay, fine. So the first thing, as soon as I'm getting the, or I can just say x to make my life a little bit easier to understand. So the first thing I will do, I will just say how many samples are there. X. Okay. And print n. So the first thing I will do is run it, compile it, negative log likelihood, and say theta. So I have to give something. So what I will do, I will do 0, 0, 0, 0, 5 zeros, and x equal to x, where x is purposefully I'm keeping it here so that no, you don't miss out what x is actually. So there are 272 data points are there in the data. Okay. Fine. Next, what I'm going to do, I'm going to read the thetas. Now, when I'm saying theta, it will be a vector of 5 values. Okay. And so let us take the first value is theta 1. Mu 1, and the function that I'm writing it is going to have a bug. Okay, and when we will run it for first time, and you will see inevitably it will throw error, but I'm writing it purposefully just to understand what is happening at this moment, so that the issues, you will not mix up the issues. Okay, once we will face the bug, I will tell you what issue is there and we will fix it at that moment. But right now, the function I'm going to write will have a bug. Okay, so theta 2 sigma 1 will have a theta 3, then mu 2 will be theta 4, and sigma 2 will be theta 5. Very nice. Then what I'm going to do, I'm going to compute these values, but instead of mean 1, I will say mu 1. Instead of 5, I will say sigma 1. Then here I will say mu 2. And here I will say, oops, let me just, here I will say sigma 2. Okay. And if I just return this guy, it should return 252 values. Okay. It should return 252 values of PDF evaluated at that X. Okay. So let me just run this. So everybody is giving me 0 because I have given a very weird value. So maybe I just give you 0.5, maybe 50, maybe 5, maybe 70 and 5. Now probably it will give some values, maybe. Yeah, now it is giving some value because the initial value that I was giving is all weird. So it was just throwing me 0, 0, 0, 0, 0. So now we can see some values, but 272. So this is 271st value and this is 272 values. Okay. So is it clear why we are getting 272 values? Because I am getting X has a 272 values. In each of those values, I am evaluating the PDF and returning it. Next thing, what I'm going to do is I'm going to take log of this guy. Okay. So I'm going to take log of F as say lnf, and I'm going to return lnf. Now you can see these are all negative after taking log because they are very small values. Very small value close to 0. You take a log, naturally you will get a negative values. But they're integers. They're all like, negative 6 point something negative. They're not very close to 0. So that's an advantage that we are having. So it will not going to face the floating point error that, okay, I have too small value, let us make it a 0. That is not going to happen. Then what I'm going to do, I'll say that now what is likelihood? Product of all the PDFs. That is what the definition that we are using, right? So if you take a log of the product, it will be sum of the logs. So we have already taken logs. So we will take here sum. If I take sum of all these values, this will give me log likelihood. Okay. So log likelihood. So let me actually, I don't want to screw up the ln. I want to use the naming convention might be create a problem. So this is the log likelihood. Actually, we are returning. So now we have to put a negative sign before that. I'm done. So this is log likelihood evaluated at these initial value of theta. I've given some value of theta. At those value of theta, negative log likelihood is estimated. It's just evaluated. I don't know if these values are the maximum likelihood estimates. These are the some possible value of theta at which the negative log likelihood is being evaluated. Is it clear to you? I mean, if you have any doubts, you should ask me at this moment. Take your time and think about it.
You said there is a bug here. Like, is it still there?
Yes, it is still there. I'll tell you the bug. Don't worry about the bug part. Okay. I'll tell you where is that, what is that bug, but the understanding what is negative log likelihood and the way I'm writing this log likelihood, have you understood that? Okay. If you have any doubt, please feel free. And you don't have to speak in English, you can speak in Hindi. I can understand Hindi, Bengali, English. These three languages I can understand. So any language is fine. Okay.
So I think
tell me.
no, the few coming steps would might lead to some questions. Till here, it's all clear.
Okay, so there is a question in the chat box. We can control least fn scale -1 as an argument in the optim function to make it maximize instead of minimize. Yeah, that is fine, but I don't want to. Yeah, if you're happy with that, so there is a Orpon is saying control least fn scale -1, and then you can make it as a maximization thing instead of minimization, solving the minimization problem. I'm fine. You can do that, but I mean, it is fine. Anything is fine. Anything else?
Sir, I have a doubt. Like the function that we are this likelihood function that we have constructed with the combination of two normal distribution. So the function has two critical points. So when we are solving this using the
What do you
maximum
mean by
likelihood,
two critical points? I don't understand that.
Sir, critical points means the points at which function changes its nature. It's same as it's used in calculus. The critical point when we differentiate.
You mean? Wait a minute. You mean?
Sir, when we
The
differentiate a
point where
function
peaks
and
are happening.
when we differentiate a function and equate it to 0, so the
Correct.
number, the
So there
solution
will be a critical point here, there will be a critical point here, and here it is
yes.
another critical point.
So there are two critical points. So generally, when we do this maximum likelihood estimation for single mode distribution, so there is only one critical point. So there is no problem with that. But in this case, there will be two critical points. So
Correct.
how are we going to decide which
Very
one to
good
choose?
question. Very good question. Okay. Very good question. And let me explain it. So when this, basically there is two mode, you are saying, right? But these two modes are on the X variable. Okay. Now I am going to optimize it on the theta. Theta is a 5-dimensional object. My x's are all fixed. Remember that. My data I have observed. Technically, I'm not going to change anything. So the values that are going to behaves here is these values. These p mu1 sigma 1 mu2 sigma 2. Okay, and that, so, and with that will effectively makes the function, the negative log likelihood function is now a function of these 5 parameters effectively. Okay. And as you says that, yes, it might happen, there could be 2 critical points and we might get stuck into 1 critical point. That might be possible. I'm not saying that is not possible. And that is one of the reason, and people try to figure out, and then question is which one is the global, which one is the real maximum MLE kind of thing. Or there could be a maximum likelihood estimates and there could be a local mode where it can get stuck. Yes, that is also possibility. We don't even know that. Okay. So that those are points can come, we can definitely face those kind of problems. Highly possible. I'm not saying that this is not possible. But it is going to be a 5-dimensional optimization problem effectively right now. And we might face a situation where we may get stuck in one mode and one local maxima kind of thing. Okay. So the question is, yes, I don't have right now the straightforward answer for your question, because the distribution itself has a 2 mode, but it might happen that this likelihood function may have a very smooth 1 mode kind of problem. So, but that we will explore a little later. Yeah, tell me.
Sir, we are optimizing with respect to the parameters. So why are we bothered about the
even in the parameter space? There could be 2 localization. We don't know.
But
In the
generally,
parameter
like,
space, there might be two modes. We don't know at this moment. We don't know whether it has a 1 mode or 2 modes. So one way of solving that issue is you plot the likelihood function and check if there is a 2 mode or if it is a single mode, or if it's a more than multimodal distribution. Okay.
So this optim function will return global maximum, correct? It will not return local.
No, not necessarily. Not necessarily.
What algorithm does the optim function use by default?
So there are a bunch of algorithms it handles. Nelder-Mead, BFGS, CG stand for conjugate gradient, Shannon entropy, Brain. So these are the bunch of, default is Nelder-Mead. So Nelder-Mead is a geometric optimization technique. Conjugate gradient will give you a global maxima if you make sure that your likelihood function or the log likelihood function is a convex function. Okay, so in this case, we don't know. This, in the case of mixture distribution, most likely it is going to be, I don't know, honestly. So we have to do some investigation whether the likelihood function has a single mode or more than single mode in the parameter space. If the parameter space itself is a more than multimodal, so then the question is which one is the, of course, the mode which has the maximum peak, that is the one we want to pick it up. Okay. Any other question? And remember that the bug is still there. Let me just run and then I'll explain you why it is there and why and how can we fix it. So first I have to give some initial value. So theta dot init. So maybe I'll just copy paste this guy. That will be good enough. And then if function fn stands for the objective function equal to, I have to give negative log likelihood, and so this is parameter, and then you give whatever the known part you give after this. Okay, and it gave me something, but it is because, but it will, it is not actually correct. It still has the bug, and it gave me something because I gave initial value very close to the likelihood estimates. That's why it converged and gave me something. Actually, yeah, it even when it says convergence equals to 0, it means it has converged. But it will throw, if I just give a little bit away from the distribution and stuff like that, then it will throw the tantrum. And I'll tell you why. Where is the problem? The problem is in optim, by default, it assumes all the parameters have a range of support between -infinity to infinity, the real line. Okay, whereas P has a support of 0 to 1. Sigma 1 has a support of positive real line, 0 to infinity. Sigma 2 also has a support of 0 to infinity. So mu1, mu2 is okay. But for P, sigma 1, sigma 2 is a problem. Okay. In such cases, and most of the time here we have a sense that, okay, what could be the possible value of mu1, sigma 1, because it's a comparatively easy problem. But there will be a time when you will not have any clue what could be the possible value of the parameter. That time, it is better if you give an initial value which is far from the likelihood value, it will throw an error. So one easy way of solving this problem that typically I use is, if theta 1 by default is setting a real line as a setup, as a support, one transformation that you can use is, this is the transformation. This is typically called logic transformation. Okay. Another, for sigma 1, you can just simply take here e to the power, and sigma 2 also you can take e to the power. Okay. Now if you run it, you see these warnings are not coming. Previously there were some warnings. Why? Because if you run again without these transformations, transformations, if you run this, there were 11 warning was there. Now, if you just use warnings to see them, what is happening? It says log f na is produced. Why log f produced na? Because it took, probably P have explored some distribution or some value which is far from 0, 1 or outside the possible range of 0, 1. At that time, f or log f have this guy has created some na, or maybe sigma 1 has taken some negative value. As a result, log f have taken some nas, and that is what it is saying. The log f have produced na. Okay, so but now if you just do these transformations, Now it's running fine without any warnings. But now P is -14, because remember that it is not the P it is estimating still theta. So in order to estimate P hat correctly, what we have to do is something like this. So what I will do, fit equal to this. So I'll run it like this, and then I have all these values. From the fit, it's an object. I will extract the estimated parameters. So fit dollar parameter I extract. So these are the first one is the P hat, is going to give me the P hat. So this will be my theta hat. Now from the theta hat, I'm going to calculate the P hat, which is theta hat 1 divided by 1, the same transformation. Remember that. It's the same transformation I'm going to use here. 1 plus exp theta hat. Now you see, oh, it is giving me actually a much worse value. Okay, let us see why it is giving me much worse value.
So shouldn't we use the inverse of that function?
The inverse of the function.
I mean, like inverse logic function for P.
No. Let me. Let me just. I don't know why it is doing that. Sometimes optimization is a bit of a challenge. Let me see what are the other parameters are doing. So the other parameters, actually other parameters are also not very well estimated, because mu1 is 72, mu2 is 70. So this transformation is actually not doing pretty well. The transformation is actually destroying the things rather in this particular optimization subroutine. So we prefer to have it the simple way of doing it. So let us just fix it in this way. Generally, it will definitely give us these warnings, but we have to leave it like this. I think we don't have much of a choice.
Excuse me, sir.
Yeah, tell me.
Sir, why are we making these transformations for exponential, and why are we doing specifically for sigma and P only?
Because in the optim, typically what happens in optim explores by default, it assumes these parameters have a support between -infinity and infinity, the entire real line. But I know that for the first parameter, P has a support between 0 and 1. So that's why we were trying to these transformations. But looks like this transformation is not actually helping us. So I decide, okay, let's not use that transformations.
So maybe like along with the transformations, we can change the initial values of theta that we're using to.
Okay, that is actually a good idea. Correct. Yeah, that's a good idea. Let us try this. So it will be yeah, that's a good idea. So then it will be e to the power log of (0.5). Log of 1 is 0, 0.5 and 0.5 1, so it will be 0. and e to the power 5. So log of 5 will be, actually that's a very good suggestion. We have to provide somewhat similar kind of thing. 1.5, 1.5. Yeah. So this might actually help us. Wait a minute. We have to run it full. Yeah. And then, yes, now it is much better. And yeah, brilliant suggestion. Brilliant suggestion. Yes. Who was it? Who made this suggestion?
Arpan.
Orpon, good, Orpon. That's a definitely good suggestion. And what it tells us? It tells us no matter what objective function, I mean, if you at least the default default optimization algorithms like Nelda-Mead or BFGS or these things, if you give you have to have some sense of value of the parameters. If you are giving value of the parameters little far from the actual parameter or the maximum likelihood estimates, then there is a likely chance that your function will not converge, and it will give you some estimates which is completely bogus. So you just cannot trust the optimization subroutine just as it is. Yeah, it was definitely very good suggestion. Thanks. So we are pretty much now we are very much on the business. Mu1 hat is equal to vector 2 sigma 1 hat equal to theta. Actually, it has to be theta hat. Yeah, then theta hat 3 xp. Then similarly, I have to do mu 2 hat sigma 2 hat, and this will be 4 and 5. All right. And now p hat is 0.36, mu1 hat is 54, sigma 1 hat turns out to be 5.87, mu2 hat is near 80, and sigma 2 hat is 5.86. Very well. Now, what I want to do is I want to use these parameter estimates in this plot. Okay. So these likelihood estimates in this plot. So I will use p hat. Mean will be, let me just, mu1 hat is sigma 1 hat, and then this is p hat again, and then this will be mu2 hat, and then this is sigma 2 hat. Okay, let us run this. Oh, I don't want p equal to 0.5 here. Let us run this. Now you can see this is definitely much better. Okay, so it has cut a bit. Let me just, what I can do, I can increase the limit y-lim. So it is between 0 and 0.04. So I can make it up to 0.05. So how I will do that? What I will do, I will just go to the histogram and I will say y-lim means limit of y is 0 to 0.05. Okay. So now it looks pretty cool actually. Okay. And looks like this indeed very good estimates that we have got. Question is, but in data science, if I just say, looking like in the visualization, it's a good estimate. Actually, it is not a very good thing. You have to give some metric and compare that, okay, is it really a good estimate? Is it really a bad estimate? How do I, so this is one model, okay? This is one model. This is model one that we have is tried. So this is my first model that we have tried. So what was our model? Yeah, two normal, mixture of two normal. Model one. Can I ask you to try the second model, which will be mixture of two gamma distribution? Second model. Model 2 will be mixture of two gamma distribution. Okay. Then model 3. So it will be model 2 will be something like this: f of x p times gamma with alpha 1 beta 1 plus 1 minus p times gamma a2 b2. Then I can say, okay, somebody can say, yeah, why gamma? I will try log gamma. Chalo, wo bhi try kar lete hain. I said, why both has to be gamma or both has to be log gamma? So I can say mixture of one gamma and one normal. That is also fine. So how many permutation combination you can create? There are, so many distribution, and why only gamma and normal? And there could be like, exponential and, who knows what. I mean, if you just open a textbook on probability distribution, there could be like hundreds of, probability distribution. People have made career on defining probability distributions. And so like, which distribution you would like to take? And all of them are probably do, some of them will be good, right? And we really don't know which actually original distribution from which this data has come. We have no clue of. So that is why again and again I'm going back to this saying by George Box that all models are wrong and some are useful. Always keep that in mind, and that will keep you humble, keep you rooted, grounded to the data. That okay, never be arrogant that again this is the best model. No, dear. If you come up with the best model, there next day another dude will come up with another best model. It never happens. So never in a race. There will be always a model which will be better than that. So you can come up with a third model, gamma A, comma B, and 1 minus P times normal with mu sigma square. So question is, now your assignment is effectively, I'm going to, so you know how to fit a model now. Okay. All you have to do, you have to write down the negative log likelihood properly, and then you have to give some reasonable initial value, right? pass it through the optimization subroutine, get the parameter estimates. If you're doing transformation, take the correct transform estimates and then do a plot and check how they are doing. And you can do the same plot on the plots on the same graph and give them a different color. For gamma, you can give a maybe green, and mixture of gamma and normal, you can give some other colors. But the question, and most likely all of these estimates, all of these estimated models will be doing very well. Some will do little bit marginally better than other, but all these models, estimated models, my educated case, will do very well, reasonably well. Question is which one to choose. So now I have 3 competing models, model 1, model 2, model 3. But which model to choose? So there is a, I think some, there is a chat saying, chi-square goodness of fit test can be used to check which is better. Okay, very good answer. Chi-square goodness of fit test. Chi-square goodness of fit test can be used to compare the model. Very good. Now there will be 2 problems. Let me tell you one problem with this. So how you will run the chi-square goodness of fit test? Okay, there is another somebody saying something. KL divergence between data and sample generated from the model. I use Theta. Very good. KL divergence between data and samples generated from the model. Generated from the model. Okay. I'll come to this later. Okay. I'll come to this later, this idea. But this is an idea, chi-square goodness of fit test, something you have already exposed in your probability statistics with R, you have already been taught. This is a part of the syllabus. So let's explore this possibility. And immediately we will see limitations of chi-square goodness of fit test. And what is the limitation? The limitation is something like this. Typically, it is a testing of hypothesis problem. And first you have to define your null hypothesis. Null hypothesis say, so model 1, I'm calling it model 1 is good versus alternate model 1 not good. Okay. So this is your test 1. Then you do another test. Another test you have to do is model 2 is good versus model 2 is not good. Okay. Similarly, you can do test 3, third test, model 3 is good, model 3 is not good. Okay. Now you do the test. So you decided I will run these tests separately. And these tests, so you run chi-square goodness of fit test. You know how to do that, right? I mean, objective observed minus expected whole square divided by expected, and then take the sum. It will give you the statistic. Then you look into the chi-square values, compute the p-value from there, and then you decide whether to reject or accept. You run the goodness of fit test. Suppose it says can't reject 8 naught. Same thing happened with the test 2. Same thing happened with the test 3. Suppose this is the situation. Now what you will do? So now you got 3 equally good useful models. One useful model is good enough. Question is which one you would like to use?
Sir, we'll check the p-values. Like,
Why p-values?
sir, like a smaller p-value is like giving us more evidence to reject the null hypothesis. So using this concept, we can check the p-values and decide.
So you want to use p-value as a benchmark?
Not as a benchmark, but like to pairwise compare the models.
They're not comparable, actually. Why? Because when you are calculating p-value, you calculating p-value with respect to this alternative. Okay. And then when you are calculating p-value for the test 2, you are calculating with respect to this alternative, and these alternatives are not the same alternatives. If you had the same alternatives, okay. Since the alternatives are different, so p-value from test 1 and p-value from test 2 are not comparable. But your approach already has the solution. You are looking for a benchmark. So that means something, you are looking for a metric which will give me that, okay, for the model 1, this is the metric. Model 2, this is the value of the metric, and the model 3, this is the value of the metric. And then we will compare these values and we'll say, hey guys, this model is better than the other 2, is at least the performing. All the 3 models are equally good, remember that. But turns out the third model, suppose the third model is better than the other model, or the second model is better than the other model. That means you are looking for a benchmarking behavior. Okay. Now, in order to solve this problem, there is a solution called Akaiki information criteria, AIC, for model comparison. Okay. So Japanese statistician and probabilist, he came up with information criteria from an information theory point of view, that how much, so when I have a data, okay, when I have a data, that data contains certain information, and I'm trying to capture or model that data information through my model. So my model 1 is trying to capture that information. Model 2 is also trying to capture that information. Model 3 is also trying to capture that information. If I can come up with that, if I can say that, okay, this is the information that is being captured by model 1, this is the information captured by model 2, and this is the information captured by model 3, and then we see which model has captured the maximum information, then we are done. Okay, so that is exactly the idea archaic information criteria actually tries to model. In the same spirit, there is something, another thing is called Bayesian information criteria. Bayesian, this is exactly same concept, Bayesian information criteria. Just formula is slightly different, but exactly same thing. You can use either of the two. Either AIC is more popular than BIC, but BIC is also popular. So don't worry about the thing. You can use either of the two. And in fact, I think AIC nowadays available in base R. Yes, it's available in base R, Akaiki information criteria. And this is the definition, the formula that they're using. -2 times log likelihood plus K times number of parameter. Okay. So more detail, I think. I think expect log likelihood. If you just write down the log likelihood, and I think you have to give the object, the fitted model, and all these things. But this is typically the archaic information criteria. K equal to 2 is the, okay. So let me just give you the formula for AIC. Formula for AIC, is -2 times log likelihood. Now here, when I'm saying log likelihood, it is theta hat evaluated at MLE times K times n bar number of parameters. Okay, and K is equal to 2. K equal to 2. And for BIC, this is -2 times log likelihood evaluated at theta hat, and for BIC it is log n, log of sample size. This is the only difference between AIC and BIC. So what is the motivation for this? The idea is basically you compute the log likelihood, negative log likelihood, and then for the evaluated at the theta hat, and then you just do some penalize for number of parameter that you are using for. So if I have a model which is 5 parameters, and I have a model which is a 2 parameters, the model which is 5 parameter model tend to do a little better than the model which is a 2 parameter model. That is being generally observed. So you have to do a little bit of penalization, and that penalization is here basically. And then K stands for the weight for the of the sort of how much weight you want to give on the penalization. Now focus on two models. I have model 1 and model 2. Model 1 and model 2. which model I would prefer. And you got a AIC for model 1, AIC 1 and AIC 2. Suppose AIC 1 is 5 and AIC 2 is 3. Just giving you a value. Okay, don't worry about this. I'm just ad hoc value. Now tell me which model you would prefer.
So one maybe because it's giving more information.
Are you sure?
Actually, the less, because we have taken negative.
Yes. We are taking negative log likelihood. Remember that. So when we are optimizing maximum likelihood, we are trying to estimate the maximum likelihood. What we are taking negative log likelihood and passing it through the optim to minimize it. That gives me the maximum likelihood. So if you are defining AIC as a negative log likelihood, then you multiply it with 2 times of the negative log likelihood, and then you are adding some penalty on it. Okay, so you would like to minimize it actually. So I would prefer a model which will have a lower AIC. Okay.
So we can see the information content also as a high information content will mean uh, higher deviation from the actual distribution.
Say it again.
Uh, a higher information content would mean that the predicted distribution is very different from the actual distribution that we are trying to predict. That's how information content, by definition, that's how information content is high. I mean, something that should not happen happens. That means we are getting a lot of surprises.
Correct. Probably, yes,
So,
you're right. That is one way to look at it. Yeah. That is definitely one way to look at it. Ayush suggested this method, KL divergence between data and samples generated from the model. This is sort of little bit less practiced method. My feeling is it will behave somewhat similar to AIC, and that is also, but it's a legitimate approach that definitely we can try out. You can compute the KL divergence between the actual data and the samples generated from the fitted model, and this is something you can try out. And my educated guess, this will also give you a metric, and this metric will, my educated guess is it will behave somewhat like AIC or BIC criteria. Okay. So a small assignment for you guys is fit these 3 models. One model is with 2 gamma and one model is with, already first model we have implemented. I'm going to share this code with you in few minutes after the class. All you have to do, you fit these 2 models, okay, and then additional model 2 and model 3, and then calculate the AIC and compare them and reach your conclusion which model you would like to use it. Okay. Any question? I think now definitely we are reaching to the end of the class. So I will stop sharing the screen. Any question so far?
Sir, Hello.
Yes, Shuli, what do you want to say?
Sir, actually, we are fitting models to some data, but sir, where to use this model? Like in case of any future predictions, can we use this model?
Very good question.
Or the aim is to fit the.
I'll tell you. I'll tell you. Let me share my screen. So I think Shuli's question is very fair. How to, okay, I fitted the model. Now what to do with this? Should I jump around? Should I?
Yes, sir. Yes, actually, our aim is only to fit the model or to use it
No,
somewhere in future.
of course we want to use it somewhere. That is main purpose. Now, how I want to use it? Suppose, for the sake of simplicity, don't take it too seriously. Suppose turns out that the first model is good model, the best model. This is the model because we have already fitted it. That's why I'm just saying. Now, how can I use it? Okay, I got a very nice, good. It's a very good question I made actually. I made a nice, beautiful plot. Now, how should I use it? In this case, I can do a inference. What kind of inference? That what is the probability? What is the probability that waiting time will be between 62 and 72? Suppose this is the question that I want to address. So how can I address this? Now I have fitted the model. So what I can do is I can write a function PDF of d mix x comma theta, and what I'm going to do is just a minute. But in here, I'm going to pass for sure the origin. I don't need actually because I'm not going to theta 4 and theta 5. Okay. And then I'm going to estimate, I'm just going to P1, mu1, sigma 1, mu2, and sigma 2. And then I'm going to return F. Okay. So density, so basically it will give me, if I give a value of X and the value of parameters, it will give me the density evaluated at value of X. If I give 60, at 60, what is the value at red line, at red curve? That will be returned. Okay. So I'm saying demix, say normal, picture of normal. So I'm calling it as like this. And then what I'm going to do, I'm going to integrate. Okay. There is it is a numerical integration method that is available. I think integrate, let me just actually keep forgetting. If equal to demix of normal, and then I have to give lower value because what is probability of basically this is what I'm looking for. 62, between 62, I want to estimate probability that 62 less than weighting less than 72, right? This is what I'm looking for. I want to estimate this. Now, how I do that? I say integrate between 62 and 72. In the range of 62 to 72, I will give PDF, fx, dx. I will integrate this. And if I solve this integration, then I will get a final answer, this probability. So my lower is 62 and the upper is 72. Okay. And I have to provide the theta, because remember that I have a theta here equal to theta hat. Theta equal to, I'll just say p hat. I'll just make sure that they're running perfectly fine. P hat mu1 hat sigma 1 hat. Let me just put it in the next thing. Mu 2 hat and sigma 2 hat. If I run this, I have to run this one. This function is not available. Yeah. So the chance that probability, the waiting time will be between 62 and 72 is only 9%. Okay. So I can say this is only 9%. So this is the kind of inference I can do using, and why I need to have this function, because how many, you can say that why I bothered, because if all I have to do, I have to check how many values are there between 62 and 72 divided by total number of values. That will give me the estimates. Very good. Yes, that is true. So what I will do, I will just check x greater than 62 and x less than 72, and I'll check how many of them are there. There are 25 of them divided by x. How many x values are there? 272. So I can just say that, okay, I will use it like this only and I'm done. Okay, very good. Then I don't have to really fit a model. What about really I want to estimate the tail behavior, maybe 95 and above or 100 and above. Okay, so how many cases are there? Really, can I estimate that I have to wait for more than 100 minutes, almost, or 120 minutes to see, or 2 hours, more than 2 hours I have to wait to watch the geyser going up? Can I estimate this probability that waiting is more than 2 hours, waiting greater than 120 minutes? Now, okay, if you want to say that, I can do that very easily, because all I have to do is x greater than 120. How many such cases are there? 0 cases. Well, because I have not, in my data, I have not even seen anything. So my estimate will be 0. So so probability is 0, but intuitively we do know that actually it is not 0. There is some probability mass is there. If we believe that this mixture Gaussian distribution actually modeling the data from where it is coming, then I can model it like this. I can say that, okay, my lower is 120, my upper may be, I give some big value, 200, and it still gives me something. It's a very small value, maybe, 3 in millions or billions, but still it gives me some probability estimates. It's very rare case. It will probably never happen, but it gives me some sense of, almost impossibility that I have to wait more than 2 hours to watch the geyser to go up. So this kind of predictive inference you can do. So that for all this, we are doing fitting this model. Is that answer your question, Shuli? That
Yes, sir. So, so if we can physically model something and we want to get some specified values, then we can choose our theta accordingly. Like we can
correct.
change the estimates of the thetas accordingly.
Correct. But the estimate of the theta has to be data driven, right? So yes, you're right that this is my distribution, but what we are doing, we are giving this p mu sigma 1, sigma 2, mu 2. These are estimated through a likelihood procedure. Likelihood are nothing but a representation how the data of the data. So under the light of the data, we are saying that, okay, these are the estimates of the parameters, and under that parameter we are trying to make some predictive inference here. Okay.
Okay, sir. Yeah, thank you.
So this was definitely very good questions. I mean, what is the purpose of fitting this model? All right. So any other question?
Sir, in this case, we have determined the mode of the data with visualization, visualizing that histogram. So is there some general technique to identify the mode of data?
Yes, just a minute. Actually, my laptop is draining the battery. Just a minute. Yes. To identifying how many modes are there is a bit of an art than science, to be honest. And that is one of the problem in clustering. So basically, if you look into these data, you will see that there are 2 modes, right, after plotting this data. But it is, we can plot this data because there are, it has only 2 variables, eruption and waiting, waiting time. Now the problem is when we go for 3-dimensional data. I mean, like if I have a 3 variables, then it's a 3-dimensional data. If I have 4 variables, then it's a 4-dimensional data, and visualizing 4-dimensional data is very difficult. I mean, there are certain ways nowadays people are trying to come up with, but still it is a difficult thing. Then there could be 5-dimension and 6-dimension things. So what people try to do is, so this is identifying or discovering the number of dimension or number of clusters or number of modes is itself sort of an art than science. And what people and in your DMML class, data mining machine learning class, Professor Madhavan probably, I think I'm sure he will address this, and that how to identify how many modes are there in my data. And we will see. I mean, if I get a time, I will probably address it sometimes, but it's almost in the zone of art than science, I would say. There are techniques are available, but those none of them are really foolproof technique, I would say. Okay, any other question? If not, then see you next week. Thank you very much for your time.